Hi, I'm Peter Quosai from Azura Associates, and I got a little obsessed with grit when I saw how many digesters were running into unpleasant surprises because they didn't know what was coming in the feedstock. Stability is critically important for a digester, and grit threatens all aspects of it. It prevents you from taking the same amount of food in every day, it prevents you from producing the same amount of gas every day, and causes unplanned maintenance that can take the digester down for a long time. So this little jar of sand doesn't seem like it's such a problem, but you see in the digester it's absolutely packed with the stuff. When it's halfway up the walls, it's causing real problems. Problems like wearing out equipment. You see this rotor pump? Well, it's meant to handle grit, but it's not meant to handle the grit that it was receiving. It was receiving grit that wasn't just sand, it had a bunch of rocks and chunks of wood in it, and that chews up those rotors. They can be replaced, but if you're replacing them every 2 weeks, then it's really hard to be making money. This digester was cleaned out after many years of operation, but in that time it had gotten over a third filled with grit. Think about that for a minute. What happens if your digester is substantially smaller than you are expecting? That's a recipe for overfeeding, for acidification, and for foaming. All of these are bad things, and they can be avoided with good process design, but all that design goes out the window if we don't know how much of the volume is filled with grit. Now we can measure how much volume is filled with grit, and we can predict, if we measure the feedstock, how quickly it will fill up. But none of these really solve the core issue of the digester is filling up, and we need to clean it out. Cleaning it out can cost anywhere between $500,000 and $2 million. Now, that's a big range, and those are big price tags. Part of that range is because each digester is different and might need to handle it a bit differently. It can be done faster if the roof can be taken off, but replacing that roof and those structures create costs. If you don't take the roof off, then you might be capturing the methane and hydrogen sulfide that it's being produced by the grit still in the digester and create a dangerous confined space environment. So what is grit? What is filling up these digesters? It absolutely is stuff like the sand that we see on the far right here, but it's also more unusual things like bits of cherry pit, bits of nutshell, little bits of wood, things that you might expect to break down but don't. We'll get to that in a minute. It's also pieces of bone and large rocks, stuff that's bulky, takes up a lot of space, and those big rocks, that's the kind of thing that tears those chunks out of the pump we saw earlier. Here's a photo of a grit sample that we took out of a real digester. We've cleaned all the schmutz off of it so that we can see a little more clearly what is making up this grit. We see that there's things like nutshells, we see bones, I see a little bit of plastic and a little bit of aluminum foil. Now those were probably broken off some food packaging in a depackaging unit and eventually made their way in here. Possibly the most damaging are sharp bits of metal. Those can be needles, razor blades. We've got a little metal shaving in here on the far left. Those are very hard and can do critical damage to equipment if they get in the wrong space. In the same grit sample, but moving all that big stuff aside, below it we have little pieces of sand, little pieces of glass, and a whole lot of eggshell. Again, this is from a food waste digester, so that's to be expected. Under the microscope, we have a real grit sample from a real food waste digester. Now, it was collected after it hadn't been in there for a very long time, but still, none of this stuff is really biodegradable. That's important for the first thing we're going to tackle. This here is a pistachio shell. This is a cherry pit, and this is the outside of some other kind of nut. All of these are examples of organic grit. Organic grit's unusual because it can be mistaken for gas potential. And what I mean by that is when you're taking a crude estimate of gas potential by measuring the volatile solids in a feedstock, you would think that all of this was going to be converted to gas when it's not. Instead, it's going to stay in the digester and just take up space. Besides those, I see there are a lot of pieces like this. Oh, that's stuck to a piece of plastic there, but there's a piece of bone stuck to a piece of plastic here. Now, in other digesters, those might make up more of the mix. Just depends on what feedstocks are coming in. And those pieces of bone can be difficult to detect because they're coming in with feedstocks that contain a lot of fat and they contain a lot of protein. The bones don't settle out when they're in that fatty, proteiny mix, but once those fats and proteins have been converted to gas, they settle to the bottom, and because they're not very dense, they take up a lot of space. Both these things are more common in food waste digesters than in farm digesters or municipal digesters, though you do still see contamination like this in both of those. Typically, in municipal digesters and in farm digesters, you're seeing something that looks a little bit more like this as the microscope is zoomed in on the stuff underneath all that bulk. Little bits of sand and glass of various sizes. So how do we know what is the grit that we need to worry about because it's contributing to how fast we need to clean out a digester, and what grit we don't need to worry about? Well, whatever makes it to the bottom is likely going to stay there. We're looking at the three main factors that are going to decide what settles out in a digester. That's viscosity, particle size, and particle density. Understanding these three factors and how they affect the grit coming into your digester can help you put in a management strategy that will make the difference between cleaning it out every 3 years and cleaning out big bulky grit, and cleaning it out every 10 years, cleaning out fine sandy grit. So I want to demonstrate that viscosity, size, and density matter to how quickly things settle out. So I've got 2 jars of, we'll call it digestate here, although it's nice and relatively clear so that we can see what's going on. Our blue one will represent a municipal digester that's pretty watery, and our green one will represent a farm digester that's pretty thick and viscous. We've got a little rock in each of those, and you can see it's going to take longer to settle to the bottom in the green one than it does in the blue one. Similarly, if we're comparing sand, which is just little rocks, and one big rock, then the rock will settle more easily than the sand does. Even if we mix it in here, some of that sand is going to stay suspended. Finally, our density matters. If we compare a dense rock and an even larger piece of pistachio shell, the rock settles to the bottom, whereas the pistachio shell moves really slowly and might even be washed out. There's a rule of thumb for the size of sand that can be suspended in a digester. For example, in a municipal digester, then sand as fine as flour can typically be ignored because it will be washed out of the digester, where significantly larger beach sand can probably be washed out in a really thick food waste digester. These can be compared mathematically, and if you're interested in specifically what particles might settle out at what size, in what viscosity, then let's set up a meeting and talk about it. Those 3 factors, viscosity, particle size, and density, are not just important in knowing what's going to settle and take up space in your digester, they're also important to know what grit management system will be effective. Grit management systems are a decision between paying at the start when a system is designed, or paying later to try to overcome difficult challenges. If you're paying at the start, then you can design an effective grit management system to keep grit out. But even if your digester's been running for many years, you can test your feedstock and know there are feedstocks that are costing you money, and you can optimize your mixing to wash out what you can. Let's start with those things that if you're operating a digester, you can do today. If you test your feedstocks, then you can make an informed decision, but each of those decisions will be taking in a lot of different factors. So we're going to focus instead on the mixing. Here's an experiment I ran with 4 different tanks at 4 different mixing energies. Each flowed one into the next, and what settled out in the bottom was what couldn't be washed out at those mixing energies. The big rocks settle to the bottom in the first tank where it's mixed like a jacuzzi. These are going to be almost impossible to remove in a digester. The next ones, that's where most of the rocks are. And if you can mix enough to suspend that size, then most of the grit will disappear. Next, we just had a little bit of grit in the next slowest tank, and that's probably a mixing level that will wash out about 25% of the grit. That might be as much as can be expected to be reasonable in a real digester. And then with almost no mixing, we see that none of the grit is washed out and that all of it will need to be cleaned out. Taking this testing information and putting it into practice, we compare the results here to calculate the cost of cleanout and to calculate the cost of mixing. If we want to mix very, very little, then it's going to cost more on cleanout. If we want to mix so much that we never need to clean out, then it might take an astronomical amount of mixing. The sweet spot is probably in the middle. Now, all of these, both mixing and rejecting feedstocks, are emergency measures. Our real methods are going to be taking the grit out either before it gets into the digester or have engineered systems in place to get it out of the bottom. To get grit out before it gets into the digester, we can either target the grit that's heaviest, the stuff that is heavier than our feedstock, or we can target the grit that doesn't break down into smaller pieces. When we're targeting our heavy grit, we're going to be targeting our glass and sand and rocks. Those will be removed by things like the hydrocyclone on the top left, which is feeding into a grit classifier, another method of grit separation, or a completely separate method on the right is our manure sand lanes. Now, the more aggressive density separation we take up, the more organics we're also going to remove, but we can get down to pretty small particle sizes that way. Here's a case where we made up a simulated grit sample. This isn't really pulled out of a digester, but it matches the characteristics of grit samples that we have pulled out of digesters, containing a lot of big rocks, a lot of glass, and big chunks of bone. You see, after it passes through a density separation system, what's left over is mostly little bits of organics and very small sand. The little bits of organics and the very small sand can probably be suspended in the digester and keep the amount that settles out to a minimum, but that will require pretty aggressive mixing. Alternatively, if we're targeting big pieces of grit that don't naturally break down into smaller pieces in the digester, these are going to be things like bone and pistachio shells, little bits of packaging, all that sort of stuff can be removed by mills and sieves and combinations of those. We mill to break things down into small pieces so that only little bits of glass and little bits of sand and little bits of bone and nutshell make it into the digester. If those little pieces are light enough, if they're not very dense, then they'll be washed out, but it doesn't reduce the amount of glass and sand. Looking at the sieves, they can pull out all the big chunks and not break them down into little bits that eventually end up in the digester. But that's also going to be trapping a lot of the organics and your fuel value with it, and it's going to be a little more challenging to dispose of than clean grit. Here's an example. This is a picture of a food waste digester grit coming from a plant that has a lot of organics in it. Now, at a plant receiving almost exactly the same food waste, but with a size separation process in place, they're able to remove all of that up front, and the digester needs to be cleaned out a lot less frequently. You can see a lot of those little bits of sand and eggshells, they're remaining. They still wear out equipment, but when they're not accumulating so quickly, it's more manageable. What have we covered so far? Well, we did a dissection under the microscope to see that there's a lot of different things in grit. And we did a demonstration to talk about how to target the grit that harms our stability the most. I mean, if we want to target the big bulky grit, then we want something that will do size separation. If we want to target the heavy grit, then we want to do density separation. If you know what's there, then technologies exist to deal with it, but knowing what's there in the first place requires testing. When looking at testing grit, I looked at a lot of different options, and I couldn't find a single test that had really reliable results and got me all of the information I wanted to know about food waste grit. So I've dug into it a bunch, and this is what I've found so far on my journey to developing a technology to test it effectively. I want something that will first inform how much it's going to cost to run the digester every day. I want to find something that will tell me how valuable these grit removal systems are and if it's actually worth the money I'm paying for it. I want to know if there are feedstocks that are costing me more just because of the amount of grit that's living in the digester, and have all the design information I need to advance the project. The first step is sampling, and sampling grit is not obvious. That's because there's only a little bit of grit in any sample of feedstock. The most effective way and most accurate way to test it, fill bucket after bucket after bucket from the feed pump and then separate the grit from that. Seems like a pretty expensive process, pretty labor intensive, but if we're taking a smaller sample from a feed tank or from a truck, then we need to be very careful about how we're doing that. Because if we miss the slug of sand that's hiding in the bottom of that truck or that feed tank, then we might come to the erroneous conclusion that there is no grit in our feedstock and be lulled into a false sense of security. Because of these challenges with sampling grit, it can be just as effective in specific situations, it can be just as effective to measure the grit coming out of the digester when it's being cleaned out or coming out of the feedstock by a grit removal system. These are biased samples, but we kind of know how they are biased, so we can still use them to make informed decisions. Exploring the different ways of testing grit, we need to start by separating it from that sample. That sample contains a lot of other stuff that isn't grit that's going to break down in the digester and going to produce gas. So how do we know what is grit and what isn't? Probably the best way is to settle out the grit. This also gives us really important information about food waste and municipal grit because their settling times are not exactly the same as their particle size. That's because there's a lot of organics mixed in with the food waste grit and thick organic biofilm coatings on municipal grit. Now these are also a little bit costly to do and a little bit complex to interpret the settling time results from. I'll try to explain why. If you have a smoothie, because our food waste feedstocks are pretty smoothie-like, then your blueberry seed in your smoothie isn't going to settle to the bottom. But once that smoothie is pumped into the digester, it's thinner, it's waterier, and that seed settles out. How we handle that difference between the feedstock concentration and the digester concentration is a level of context that needs to be included in your results, or it will be difficult to interpret how they were created. Another important thing to test is your particle size. It might be sufficient to test the particle size alone if most of your grit is sand, in certain municipal cases and in manure cases, but it can also be a good supplement to the settling time for food waste grit. Finally, if we're just testing sand-laden manure, then there is a bit of a shortcut we can use. Because we know that the manure is just manure and doesn't contain digester grit, then we know all of the sand is just sand. So we're going to burn away all of the organics and be left with an ash. Then we're going to wash the ash in acid to remove all of the salts. At the end, we should just be left with any sand that was added to the manure. Now, this is much faster than those other methods I mentioned. It provides pretty biased results, and we can only use it in that manure case because food waste grit and municipal grit have such varied characteristics. These methods that I mentioned are separating the grit from our feedstock as well as capturing information. Once we've separated it, we need to measure the bulk density, particularly for food waste grit, and I'll show you why. These 4 jars all have 80 grams of grit in them. This is 80 grams of sand, and it doesn't take up very much space in the digester. This is 80 grams of glass. It takes up noticeably more, but not nearly as much as the 80 grams of bone or 80 grams of nutshells. If your digester is filling up with nutshells, then the important information is how fast you're losing volume and not how much those nutshells weigh. Regardless of how you're testing your grit, at the end of the day you want to know that you're getting the answers that you need to make informed decisions. A pretty typical grit test result might be a particle size distribution, like we see on the right here. Now, that's useful in designing a grit removal system, but it doesn't tell us how many years it's going to be until we need to clean out again. It doesn't tell us if we're losing volume every time we add feedstock to the digester, and it doesn't tell us if our grit removal system is meeting the requirements set out in our contracts. These are the kind of answers that the tests that I'm discussing are trying to attack. Are you at risk? Well, bad news is that all digesters accumulate grit. And the good news is that some almost never need to clean out. Where you fall in between those depends on your feedstock. It depends on those viscosity, particle size, and density factors. And if you test these, then you can find a grit removal system that is effective and will keep your digester stable for many years. I hope that this video has provided some of those tools that you need to ask the right questions and find the right technology. Thank you very much.